Welcome back to the DSA series again. Today we are stepping into time complexity. What is it and how we calculate it and how it works? And how to stop your algorithm eating up your old memory in your system. Alright, when we analyze algorithms, we usually measure this, how fast code runs, and by space complexity is just critical. It measures how much memory your algorithm uses. A lot of beginners only focus on stopwatch but ignoring space is just a massive scale. So why space matters? It's when we analyze algorithms and we usually measure time, how fast the code runs. But why does space matters? Because memory is finite. An efficient algorithm on your background can cause memory overflows that kill production servers. And on a mobile app, excess memory urge wrecks performance and drains the user's battery. So, when we talk about autonomy and memory, before we count memory, we need to know where it lives. A running program uses 4 memory segments. The stacks for function calls, the heap for dynamic object and arrays, and the code for program instructions and executable code, and the static is global and static variables. So, the stack is like function calls. So that stores local variables per call frame. And it is strictly operates strictly on last in first out, which is we also known as LIFO queues. LIFO queue basis is the best part is auto-freed. Memory is released the second a function returns. So when we talk about heap, then this is for dynamically allocated objects and arrays created in runtime. So unlike this stack, it requires a garbage collector of manual cleanup for a free up memory. And because of this flexibility, heap access is slower than stack access. So, space equation. So, how do we calculate the space complexity? It's simply your input plus your auxiliary space. So it's where we are getting the total space complexity by calculating input space plus auxiliary space. So that's it. That's how we calculate space complexity. So what about input space? Input space is a memory required just to hold the data pass to your function. But here is the secret. Interviewers typically exclude input from your final analysis. Auxiliary space. So what about auxiliary space? We talked about earlier. What interviews actually care about the auxiliary space, especially when you're facing interviews or whatever. This is the extra memory you create, like new arrays or maps. Beyond the initial input, this is the true measure of your algorithm's efficiency. So it creates an extra memory you create. Also, interviewers care about this. Let's look at the common complexities. Bigger one constant space means you only use a fixed few variables, and the memory never grows regardless of input size. And bigger and linear space happens when you create an array that scales proportionally to the input. And bigger and squared quadratic space usually looks like a 2D matrix. Try to avoid this in interviews. Now, for the silent killer, recursion. Recursion is not free actually. Even if you don't create new arrays, every recursive call pushes a new frame into a call stack. In memory, if you create n times, you stack n frames, and this is automatically big O n auxiliary space. So when we call about visualizing is call stack, it simply means pushing into the next step in a stack. let's visualize this. Imagine function file calls function 4, which calls function 3. See this? And so on. Every single call pushes a new block onto the stack, and each of these blocks holds its own all local variables and execution content. Memory is filling up so fast. And another silent killer is stack overflow. If you forgot your base case and the recursion goes too deep and the call stack runs out of all memory, what is the result? Stack overflow, and your memory will be filled up and your program completely crashes. But if you write it correctly, you hit a base case once that happens, and recursion stops. The stack unwinds, popping out frames from the bottom up. Memory is releasing back to the system, and your space complexity returns to the baseline, as you see in this visual. So let's apply all of this for real into Recursion. Reversing an array, how do we do it efficiently? What is the space cost? The first one is naive approach, big O in space. So here is the brute force method. We create a brand new empty array, iterate backwards through the input and copy each other element over. This works, but it takes a big O and auxiliary space because we literally build a second array on memory. We are literally wasting memory, as we done earlier. So this is kind of memory wasting. But when it comes to optimized approach, bigger one space. Now look at the intervening solution. The in place to pointer method. We use left pointer at index 0 and a right pointer at the end. So we simply swap elements and move the pointers inward until they meet. No extra arrays needed. So in here we don't need extra arrays because we only use two variables. Our auxiliary space is bigger one. So, and that is space complexity. Respect the memory and write better code, and I will see you in the next video.